In the last lecture, we are discussing about the partial derivative, and I teach you how to find partial derivative of the function into variable. I told you the difference between constant multiple and when you dip constant, and the thing that we are working in the last lecture is about we have the function into variable like this one, and we like to find fx and fy. The next thing that I like to do is going to be, I'm going to give you more example for the partial derivative, and I will do the higher order partial derivative, and I will explain the meaning of the partial derivative for you. In example 6, you have fxy equal to 1 plus e to the y sine x. So when you like to find fx, this one turned out to be d dx of 1 plus e to the y sine x. And if you see the structure for this function, the function in x that you are differentiating is on the exponent, and on the bottom here is going to be 1 plus e to the y, and this guy turned out to be constant. So we are having the function of the form d dx of constant raised to the ux. Okay, so it's going to be constant raised to the ux. And this one, when you dip something like this, you think about the thing that we study, exponential function. The exponential function is the one that we studied last semester, dip a to the u. Okay, when you dip a to the u, it's going to be a to the u log a and du dx by using the chain rule. So this one is the exponential function. So for this one, it's going to be d dx of constant raised to the ux. And I'm going to have the following formula for you. So this one is going to be the whole thing, which is constant raised to the ux. Okay. And you will have log constant, and you're going to have the partial derivative with respect to x. So it's going to be, let me move this one a little bit. So this one is going to be log of that constant, and you have du dx. Okay. So for this one, you're gonna have log constant like this, and it's going to be ux up here. Okay, so let's try one example before we go to the thing that we are having. So if I ask you to find the dx of just 10y to the x squared. Okay, so if I have 10y to the x squared, the thing that you should be able to see is going to be x up here, and this one you have 10y down here. So in this case, I'm gonna say that this guy is expo. Okay, so like I have here, so this one is gonna be expo. It's short for exponential function. And when you like to find derivative of this guy, it's gonna be the whole thing. Okay, so it's gonna be 10y to the x squared, copy, and you have log of 10y, and you're gonna differentiate x squared, and differentiate x squared will give you, okay, so differentiate x squared will give you 2x. Okay, so this one will be 2x. Okay, So this will be your derivative. So for our ddx of 1 plus e to the y sine x, so for this guy, we're gonna just have 1 plus e to the y log 1 plus e to the y. Okay, so log of the green guy down here. And you're gonna have to differentiate sine x with respect to x. So we have tan y to the x squared log tan y dx of x squared. So it's going to be 2x. So this is the thing that you have. And the thing that we are doing here is going to be you need to differentiate sine x. So differentiate sine x is cosine x. Okay, so derivative of sine x is cosine x. So you're gonna have 1 plus e to the y log 1 plus e to the y times cosine x. Okay, so that is going to be your final answer for fx. So the thing that is going to be our key idea turned out to be this box. Okay, so it's going to be derivative in terms of exponential. The next one that we like to find is going to be derivative with respect to y. So we like to also find fy. So the thing that we would have will be d dy of 1 plus e to the y to the sine x. Okay. And you see in this case that the thing that you are differentiating will be the function in terms of y, and you have constant up here. Okay. So you see that this one look like the formula of the power function or the power rule that we used to have in Calc 1. So when you have the dx of u to the n, so it's going to be n u to the n minus 1 and du dx. So this one is the power rule. And when we are dealing with the power rule, the function turned out to be d dx, okay? And d dx of function in terms of x, so it's going to be gx, okay, or ux, and raised to the n power, okay, so raised to the n power. So it's going to be just n, and you have dx to the n minus 1, and you have the dx of the inside, which is gx in this case. So this one is going to be just you use the power rule. Okay, so this one will be the thing that we are using right now. So okay, so that will be just the power rule. So for example, let me also give you one example before we move on. So for example, if you are asking for d dx of 1 plus root x to the 10y like this. And you see that it's gonna turn out to be, okay, for this one it's gonna be power room, so it's gonna be 10y, okay, so it's gonna be 10y, and you have 1 plus root x to the 10y minus 1, okay, and you find derivative of the inside 1 plus root x, okay. So in this one, you're gonna just have the final answer in terms of 10y, and you have 1 plus root x to the 10y minus 1, and you dip 1 plus root x, so it's gonna be just 1 over 2 root x. Okay, so that is gonna be the power rule. And you're gonna have to find Fy for me here. So this one we will apply the power rule. So you see that this one is gonna be function in y and you have constant up there. So you're gonna just move the constant down. So it's gonna be psi x, and you have 1 plus e to the y, and you have psi x minus 1, and you find derivative dy of 1 plus e to the y, okay, and this guy will be psi x, you have 1 plus e to the y, psi x minus 1, and you find derivative of 1 plus e to the y, so it's going to be 0 plus e to the y, and this one will turn out to be your final answer. Okay, so let me resize this guy a little bit. I like to have them on the same page. Okay, so that will be our example. So the thing that I like to conclude will be, it's turned out to be two cases. It's going to be about constant to the ux. So this one is going to be exponential function that we're going to use the derivative in form of the exponential function. Another one will be just using the power function. So it's going to be the dx to the n here play the role of constant in this case. Okay, so this n play the role of constant. Okay, sometimes constant present themselves in the fancy way, like you see that the constant in this case turn out to be equal to psi x, so it's going to be 4-letter constant. Okay, so that will be our example 6. Okay, so let's do something else. So we have fxy z equal to z squared secant y log x plus cosine z to the y. So you see that this one is a function in 3 variables. So you have variable x, variable y, and variable z. So you have x, you have y, and you have z. So for this one, you're gonna have 3 partial derivatives. So we have the derivative with respect to x, derivative with respect to y and derivative with respect to z. Okay, so it's gonna turn out to be 3 derivatives. The idea for doing derivative in each variable turn out to be simple. When you like to find derivative with respect to x, so you're gonna have y and z are constant. Okay, and if you like to find fy, so you have x and z are constant, and you have fz is gonna be x and y are constant. Okay, so for each variable, you see that if you like to find fx, you're gonna think that y and z are constant. If you like to find fy, it's gonna be x and z are constant. And if you want to find fz, it's gonna be x and y will turn out to be your constant. So it's gonna be like 3 cases and 3 partial derivatives in this case. So you're gonna have fx, okay, fx. So you're gonna have y and z are constant. So it's gonna be dx z square sec y log x plus cosine z to the y. And you see that the thing that you're gonna differentiate turned out to be just x. So you see, it's turned out to be only one term that you're gonna take care. So for this one, this guy turned out to be constant. This guy turned out to be constant. Okay, so you have constant and you're gonna differentiate them as you have constant. So you're gonna just have z square secant y and you have the dx of log x. Okay, and you're gonna add by the dx of cos z to the y. Okay, and this guy, when you differentiate, is gonna give you 1 over x, and you just copy the front term down, so it's gonna be c square and sec y. Okay, so it's gonna be z square sec y times 1 over x. So this guy is just this term, okay? And you have this one, which turned out to be constant. And you dip constant, you would just get 0. Okay, so you find derivative is gonna turn out to be 0. And that's it for the partial derivative with respect to x. Okay, so you see you have y and z are constant. The next one is fy. Fy that let's use other color. So for fy, it's going to be dy of the same term. So it's going to be z square secant y log x. Okay, and you have cosine z to dy. Okay, so for this one, you're gonna find derivative with respect to y, and the thing that you're gonna differentiate turn out to be 2 terms. So you're gonna have y up here. So you're gonna get the dy, okay, for the first term. So you see that you have constant for z square, and you also have constant for log x. So for this one, you're gonna have z square log x, okay, and you're gonna have the dy of secant y, okay, and it's gonna be the dy of cos z to dy, okay, and so it's gonna be z square log x, and dip sec y, you're gonna get sec y tan y, okay, with respect to y. So this guy will be just this term, okay? So dipsec is secant, okay, like we had for calculus 1. And you're gonna differentiate the second term. So you see that you have constant to the function. So this one turned out to be exponential function. So for this one, it's gonna be just, you have the whole thing cos that to the y and log of cos that, and you find derivative of y with respect to y, this one, okay? And dy dy, this guy is equal to 1, okay? So this guy is equal to 1. So your final answer turned out to be just only this term. So it's gonna be z square log x sec y tan y. Okay, so let's put parentheses. And you have cos z raised to the y log of cos z. Okay, so that is going to be your fy. Okay, I will let you do fz on your own, and I give you the solution during the recitation. Okay, so it's going to be dz of z square sec y, okay, log x plus cos z to the y, and for this one you gonna find derivative of these two terms. Okay, I'll let you do this one on your own first, and we're gonna discuss this one during the recitation. The next one is going to be about the higher order partial derivative. In calculus 1, you have y equal to fx, okay, and you have derivative. So you'll be able to find f prime x. So this guy is called derivative, and this one still a function. So we be able to differentiate this guy again. So you would get derivative with respect to x again. So it's going to be f double prime. So this one you dip, okay, and this one you also differentiate. So this one is going to be second derivative. However, for calculus 2, you have stat equal to fxy, okay, for cal 2. So you have stat equal to fxy, and you have two choices for derivative with respect to x or with respect to y. So you have two partial derivative. So this one is first partial derivative. Okay, so in this one, it's going to be, okay, so you have first partial derivative, and first partial derivative turn out to be this guy and this guy, okay, with respect to y and with respect to x, and they are function, okay, they are function. So we're gonna be able to differentiate this guy and this guy again with respect to x and with respect to y. So you see the notation, okay, let me enlarge this one a little bit. You see the first derivative that I use the orange color. So you see this one, you have the orange color, and you differentiate with respect to y. So, and with respect to x. So you see this one is second order partial derivative or second derivative. So for this one, it's gonna be second partial derivative. Okay, so it's gonna be second partial derivative. So you have derivative with respect to x, derivative with respect to y, and the notation that we use, we're gonna read from left to right. Okay, so we're gonna read from left to right. So it's gonna be inside out like this. So it's gonna be first x, second x, and this one is first x, second y. Okay, so this one is a notation in the subscript way. We have another notation in terms of fraction way. So you see when you have this guy, it's gonna mean that you differentiate with respect to x twice. Okay, so you differentiate with respect to x twice. And for the second partial derivative in the fraction notation like this one, so you see that when you read it, it's going to be from right to left. Okay, so this notation means that first you differentiate with respect to x and you continue differentiate with respect to y again. Okay, so this one look like that. And the thing that you have to notice will be this guy turn out to be dy, and you have dz dx. Okay, so it looks like this because of this. However, on the other side, you just have fx first and then you continue with y. So you see that the notation turned out to be kind of different. Okay, so when you read this notation, please be careful. Okay, one is going to be left to right and one is going to be right to left. Okay, similarly, if you begin with fy, so you see that you have fy and you can differentiate fy in two ways. So you'll be able to just differentiate fy with respect to x and with respect to y. So this one is gonna turn out to be second partial derivative. And when you read this notation, this one will be from left to right, and this one is gonna be from right to left, same as above. Okay, and you have fyy, which is you differentiate the function z with respect to y twice. Okay, so this one is called the second order partial derivative. We can have third order or something that I'm going to mention later. Okay, so for this one, we like to find the second order partial derivative. So you have fxy equal to x squared y to the third plus root x log y. So we gonna find fx and fy first. So you see that in order to find second order, okay, in order to find second order partial derivative, we would just need first order. Let's find first order first. So you have fx and fy, okay? I'm not gonna step by step with you anymore, so I'm gonna differentiate this one. So it's gonna be 2x, 3y y to the third, okay? Plus 1 over 2 root x times log y. Okay, so that is going to be our partial derivative when you hold y is a constant. And for fy, it's going to be x squared, and you differentiate y to the third, you get 3y squared, and differentiate log y, you get 1 over y. Okay, so that's your fy. And from both of this guy, you gonna differentiate this guy again with respect to x and with respect to y. So you see that you're gonna have fxx, okay? So you're gonna have fxx, so you get 2y to the third, okay? And 1 over 2 root x is 1/2 x to the negative 1/2. Okay, so it's going to be 1/2 x to the negative 1/2. So for this one, it's going to be 1/2 and it's going to be negative 1/2 x to the negative 3/2. Okay, and log y is constant. Okay, so it's going to be fxx. And similarly for fxy, we're gonna differentiate with respect to y for this guy. So it's gonna be d dy of this guy. So you see that it's gonna be this guy come down. Okay, so it would give you 2x and 3y squared plus 1 over 2 root x, okay, and you dip log y, you get 1 over y, okay, so that our second order partial derivative, and you have fxx and fxy ready for you to compute. And the next two will be you're gonna differentiate with respect to x and y again of fyx and fyy. Okay, so you see fyx is going to be, you differentiate fy with respect to x, in a dip with respect to x. The thing that you get is going to be dip this term and dip this term. So this guy will be 2x. This guy is going to be 1 over 2 root x. Okay. So for this one, it's going to be 2x, 3y squared. Okay. And you have 1 over 2 root x, 1 over y. Okay. So that will be fyx. And for fyy, it's going to be, you're going to differentiate this guy with respect to y. So you see x squared stay constant, and you're going to just dip 3y squared. So it would give you 6y, okay? And you dip 1 over y. Dip 1 over y in this case is y to the negative 1. And it would allow you to just get negative 1 over y squared. Okay, so that is going to be the formula that I ask you to memorize from calculus 1. So it's going to be root x and 1 over y squared. Okay, so this one, if you recall, is derivative of 1 over y is negative 1 over y squared from calculus 1. Okay, so this is the final answer. So you're gonna have 4 second order partial derivative. The thing that I should mention here that you can see is gonna be, hey, you have fxy and fyx are exactly the same. Okay, so it's turned out to be the same. Is it coincident or is it always true? The answer for that is it's kind of always true, but it's not always. It's often true. It's going to be fxy equal to fyx when you have nice function. Nice function means continuous. Okay, nice function means continuous. If you have the function that you have formula like a power, like a log, like a sine, like a trigonometry function, you would get fxy and fyx exactly the same. Okay, so as you can see here, they are the same. Okay, for second order. And the thing that different turned out to be fxx and fyy. Okay, that is you cannot control. However, these two guys are the same. I'll just ask you to find both of them basically because it's gonna help you in order to check your solution. If you get these two guys not equal, okay, you might do something wrong. Okay, so that is gonna be my suggestion. Okay, for this one, you have if xy equal to log 3x plus y squared. So we like to find the second order partial derivative. So let's find first one. You have fx. You dip log, it's going to be 1 over 3x plus y squared. And you dip inside, you get 3. Okay. And you have fy. So for fy, it's going to be 1 over 3x plus y squared, and you have 2y. Okay, so you differentiate with respect to x and with respect to y. So you see when you have 3 here, it's come from d dx. Okay, so it's come from d dx of 3x plus y squared, and you have 2y here. This guy come from the dy of 3x plus y squared, and they are not the same. Okay, so that my fx and fy respectively. Okay, so I just want to mention that this guy come from these two different guy. Okay, so I would ask you to find fxy, fxx, and any other function for me. Okay, so I would just ask you to find this guy and this guy, this guy and this guy. Okay, so this one I ask you to find fxx, fxy, fyx, and fyy for me. Okay, for your I like you to do this one first, and I'm gonna give you the solution during the recitation. Okay, so please find for this for me. The next one, okay, so the next one, you have if xy equal to sine y tan x, x squared plus 3 to the y, and the question asks you to find f x, y. So for this one, I give you the guideline that you have to find fx first, and then you're gonna find fxy. Okay, so it's gonna be first order and it's gonna be second order. Okay, so that is gonna be two kinds of derivative. Okay, you do this one on your own first. Okay, and I give you the answer during the recitation. And for number 13, you have if x, y, z equal to sine x z plus y squared, and you like to find if x, y, z. So for this one, it would be you find fx, okay, find fx. You dip side is going to be cosine xz plus y squared, okay, and you dip inside with respect to x. So this allow me to have cos xz plus y squared times z. Okay, so this guy, you see that it's going to be equal to z plus 0. Okay, so it's going to be just cos xz plus y squared times z. Another thing, you have if xy, so you're gonna continue if xy, fxy, so you're gonna get the dy of cos xz plus y squared times z, and you see that your z here is constant. Okay, so your z here is constant. Yeah. So you allow to just pull out, and you're gonna differentiate only this function. So you did cos, you get negative side, and you have xz plus y squared, okay, and you're gonna differentiate, okay, so you're gonna differentiate the inside, so you would just get with respect to y, so you get 2y. Okay, so this guy come from the dy of xz plus y squared. Okay, so this one is the gray one. Okay, so it's gonna be 2y. Okay, so that will be my second order partial derivative. And for the last one, you would want to have the third order. So it's gonna be f x, y, z. So you're gonna continue finding derivative with respect to z. Okay, so you're gonna group this one as negative 2yz, one group, and you have psi of xz plus y square, another group. And you see that this one is product. Okay, so you have the function set, and you have set here, and you have set here. So it's turned out to be product between two functions in terms of set. So you just apply the product rule. So from the product rule, you would get the first derivative of the second, okay, plus the second derivative of the first. Okay, so it's going to be this one. Okay, and you continue, so it's going to be negative 2yz. Deep side, you get cos xz plus y square. Okay, and you differentiate the inside, you get x. Okay, so that is going to be this term. The second one, you have psi xz plus y square, and you differentiate, so it's going to be negative 2y. So this one come from the thing that we use is the product rule. Okay, and you have the first derivative of the second plus the second derivative of the first, and this one will be the final answer. Okay, and you see that you have derivative of, you have x here come from, you have x here come from derivative of, okay, so x here come from derivative with respect to z of xz plus y squared. Okay, don't forget this term, and this one is kind of easy to understand, I believe. If you be able to differentiate from calculus one, this one is going to be the thing that you'll be able to do quite quick, okay, and you'll be able to understand quite quickly. Okay, I will stop here. The next clip will be about the meaning for interpretation of partial derivative, and it's going to be about the approximation. Okay, so that is going to be on the next clip. So this clip is going to be more example on partial derivative. I ask you to be able to do exponential function in terms of a fancy constant, or the power rule in terms of a constant like this. Okay, so you have constant which turn out to be, sometimes turn out to be psi x like you see here. Okay, and I ask you to be able to find the second order partial derivative for, it's going to turn out to be 4, and you must notice that these two guys always the same. Okay, so for like a finite function, if f is nice, if f is nice, I would say nice, then you would just have f xy must be equal to f yx. And please try to find this second order partial derivative for me for example 11 and example 12. Okay, we're gonna discuss this one during the recitation. Okay, so try to do this one. If you have it correctly, it means that you understand this topic, and it's going to be helpful a lot for your exam 3. Okay, so that's all for this clip.